Welcome everyone. Today we're going to look at some cryptography, some encryption information. They lead us off by talking about the Caesar cipher, which is a really good way to explain what you're trying to do. You have a message like, don't buy the beef. I don't know why that would be a message, but you have that message and you don't want anyone to know what's in the message. And so you have to figure out a way to scramble the message basically. And you may have done some of this in school where basically they give you up at the top, 4 is something and 3 and 7 is something. And then you have to go through this math problem and figure out what it's actually meaning. Well, in the cipher of Caesar, basically he would take the first letter that he's dealing with and then substitute the third letter down. So A became D, B became E. So you could take a message, write it all out, and then go through the process of replacing that information. That way, when somebody got that message, if they intercepted it, they'd go, what is this? Now, that's a really simplistic thing. And after a certain amount of time, you would be able to figure that out. But it would take you time because you wouldn't know what did they do to scramble this. However, looking at it, you should be able to start to tell maybe every letter's been moved by one. So if you could find one word in there and say, oh, this is a the. If you can find that, then you can solve it, right? And then you can basically decrypt the message. So that's the idea. You take plain text and you mix it up, encrypt it, and you use a key that only you can understand or the computer can understand or the receiver can understand. And that's how encryption works. So right now, this page is being shown to us. We can read what's on it, but I access this page. You can see the little lock here, HTTPS, which means it was encrypted with SSL, secure socket layer encryption. So in order for that to work, the test out website over there has to encrypt it with the key, and then I have to have a key to decrypt it. And so the only, I'm getting ahead of myself really, but the only real problem with that is if it's the same key, then somehow I have to get the key. And that could be a problem with making sure that it doesn't get seen. Anyway, two terms, data at rest and data in transit. Those are pretty self-explanatory. It just means that data at rest is sitting on your hard drive. It's sitting on your flash drive. It's not doing anything. You're not using it. It's just sitting there. It might be on an optical disk, whatever. And you can encrypt things using full disk encryption. So most operating systems will include the ability to encrypt files on them, which you get a chance to do in this section. And then, of course, data in transit means that we're sending the data. So we're taking the file that was just sitting there, and now we're sending it. And how do we make sure it's encrypted there? And of course, an example is Hypertext Transport Protocol Secure, HTTPS, and using a virtual private network, which is encrypting the entire channel, not just if you're connected to someplace that has encryption. So there are encryption standards out there. Encryption algorithms scramble signals to make them unreadable to anyone who doesn't have the correct key. And that's basically the way it works. Encryption is really strong. It really is. The ability to encrypt something and protect it is running ahead of the ability to decrypt it, meaning that encryption is secure. It's usually very secure. As a matter of fact, most of the problems with encryption that have been found, like, oh, it's no longer secure to use whatever encryption, is usually they hack the process of encrypting it. And then in that process, because they've hacked that, now they have access to the encryption. So anyway, one way an attacker tries to find a key is just to try. That's what brute force means. It just means I'm going to pound it. I'm just going to try. They try any possible key that may work. And so if you have a very, very small key, maybe a 4-digit key, then it's not going to be hard to decrypt it, because in four digits, then you only have certain, how many variables is that? I don't even know. How many different iterations of that is it, I should say. So in 1977, IBM developed DES, which is a data encryption standard, and it used a 56-bit binary key. So meaning, right, it's binary or ones and zeros. So each key could have one of 72 quadrillion possible values. And it worked for a long time. But in the late 90s, computers had become powerful enough that they could just run through all the possible combinations. And that's a lot of possible combinations, even though it would take a few days for that to happen. So then it's like, oh, we got to do something else. So in 2001, they came out with advanced encryption standards, AES encryption, and that can be up to 256 bits long. So understanding this 56-bit as opposed to 256-bit, you realize that's a lot more bits that we're dealing with, which would take a modern computer trillions of years to brute force. So if we're using 256-bit encryption, a modern computer would have to sit there and work on that and run through every iteration. And maybe it would get lucky in the first 100 years, and maybe it wouldn't. It would take trillions of years for that to happen. So that whole thing you see on TV, oh, just a minute, I'm figuring out the numbers as it goes along. Yeah, that's not real. It's not how it works. It's not how it happens. It's not how hacking occurs. So if it's a low enough encryption, then hacking will occur, right? If it's too big, then that's just going to take too much to actually deal with, and then we got to figure out a different way to get into that message. So Wi-Fi encryption, there's a few standards. WEP is the old one, and you could hack that within, and I'm not joking, we did it in class back then. You could hack it in like 16 seconds. Enough data gets transmitted and you see the key and you get the key and then you're in. Now we're moving beyond WPA2. So this has WPA2, which replaced WPA. And I talked about that in another video, that basically this was so bad they needed to do something. And so as WPA is being made, they went ahead and adopted it and started pushing it out. And then WPA2 came out after, which is a much better standard. There's problems with this encryption method. They have found holes in ways that people can break into WPA2. And so WPA3 solves those problems, at least for now. So what you would want to do, why you would care about this information is obviously if you're going into the security stuff, you care. But if you're going to buy this stuff, you're going to go out and get a router, a wireless router, you want one that says, I can do WPA3. Usually the Wi-Fi 6 versions are usually WPA3 capable. Anyway. And then it talks about email encryption. It talks about the HTTPS, which uses secure socket layer to get that done. And they tell you a little bit about that. We're going to move on and take a look at, oh yes, I need to look at some asymmetric encryption. So let's jump over to my photos here so we can start to dig in a little on that and show you a little more than, well, actually I haven't watched the video on this. So maybe they tell you what I'm going to tell you, but I don't think they do. All right, so basically, as I said, you know, if I'm talking to test out over here, and this is secured, not through the VPN. I know this says VPN here, but that's not turned on. So I'm using HTTPS. That's what that little lock is going to mean for me. If that's encrypted, then how did it get encrypted? Well, there's two ways. There's symmetric and asymmetric encryption, often called public key encryption or public key cryptography. You see all that on the screen. Here's public key cryptography, here's private key encryption, and public key encryption. So there's different terms that they're using. And public key sounds like it's less secure. You know, if the key is in the public, then is that more secure? It doesn't sound like it is, but it is. It actually is. Because what they're telling you is asymmetric encryption. So again, the term asymmetric means that we are not synchronized. We're not synchronized. Synchronous means it's synchronized, and asymmetric means it's not. Symmetric means it's synchronized. Asymmetric means it's not. So in this case, this public key cryptography or public key encryption, showing it here, is you end up with these two keys. And so in any encryption that's done with public key, or as they say, asymmetric encryption right here, anything that's done has to have this key pair. It has to have a private key. This is Bob's private key, and it has to have a public key that's given to the other person. So in order for this to happen, we'll say this is Bob and Sue. Then when Bob wants to, oh, it's Alice. Alice is actually sending it. Alice has Bob's public key. She goes ahead and writes the message and encrypts it with the public key. It turns it into garbage, that nobody can understand if it's picked up in transit. That's what I want to say. And it's decrypted with Bob's private key. Now, the private key never goes anywhere. It never gets sent anywhere. It never leaves Bob's side. This is never exposed or seen by anybody, but the public key is. Now, this key pair enables basically Bob to say, okay, I think we've been hacked here. I am going to discontinue this public key and create a new one. And then that way, anything that's coming out now has a brand new key that it's being used with. It's very, very secure this way. So when you really look at this public key cryptography or asymmetric encryption, what's going to happen is Bob has a private key and public key, and Alice has a private key and public key. And then that way they can communicate back and forth with no problems. And if there's ever an exposure, the private key is never exposed. It's always the public key. They generate a new public key and move on. This is the type of encryption that's really, really hard to break and what we'd like to use in most situations. However, in a lot of situations, you can't use that. There has to be basically a shared secret key. And so in lots of situations, like here we are with test out, they're going to use a private key encryption or a symmetric encryption, meaning that it's using the same key to encrypt and decrypt. It's using that process. That means somehow the shared secret key needs to get to the person. This is very, very secure if you actually give it to them on a flash drive, right? So if we're together and we're like, okay, we're going to have to use this encryption to make sure we don't get caught in all the legal activity that we're doing. So here's the private key. And the person puts it on their computer, and then you put it on your computer. And that way you both have the key, and the key doesn't need to ever be transmitted through the data channel. However, if that's not the case, like I'm logging into test out and I don't have it, the test out's going to send me that key, and then I'm going to get the key, and then we can talk encrypted. And of course, when that happens, there's that possibility that that key might be grabbed if somebody was watching it. So that's the difference between private and public key, or let's see, private and public. So symmetric and asymmetric. I need to get both of those right. Right. So symmetric means using the same key. Asymmetric means using different keys. And that's here in the video right there. And then certificates are totally, totally different. Certificates are proving you are who you are. So a lot of times you'll go on a site and it'll actually tell you this site has got a fraudulent certificate. Do you want to go there? And they tell you you shouldn't go there. Something's wrong with their certificate. Not all sites and not everyone has these certificates, but if you're a big enough company, then you have a certificate. And that certificate is basically a third party that's saying, yeah, that's Microsoft, or yes, that's Google. And then that way, when you connect to Google, they're sending you their certificate. Your machine is looking at the certificate, asking the third party, is this Google? And they say, yeah, that's Google's certificate. And it's a way of verifying you're talking to the right person. Because, right, you never see Google face to face. So are you really hitting their site, or have you been sent to somebody else's site? And trust me, there's ways to get that done. And so when you see those fraudulent certificates, or the certificate's not up to date, that's a big concern. So certificates are not really encrypting things. Certificates are a way to prove you are who you are. And anybody can go and get certificates. It costs you money. And internal networks will use certificates where they give their own certificates out to the different machines and have their security, where basically one machine is being contacted by another, and then that machine that's being contacted is like, hey, I got this certificate from James McBride's computer. I'm going to go talk to the server. The server says, yeah, that's James's certificate, and we're good to go. So there's public certificates that we see on the internet all the time. And then people, internal systems will use them on LANs and such. And let's take a look at password facts. Most people are aware of the password best practices. I often will talk about this in class and actually ask people to start thinking about their passwords. It's very hard for us just to remember random junk. Some people can do it. My wife can do it. I could say, oh, the password for this is some random junk. Here you go, dear. And she'll remember. She'll be like, oh, I think it was L765_72. I can't do that. So most of us will pick something that helps us remember. And the thing is not to expose that too much. And most people will do something very easy. I would guess that most students that are coming out of high school use whatever their password was in high school. A lot of high schools will just make that the person's student ID. And so if you can gather what their student ID was just by talking with them, when a lot of people won't realize, hey, I just gave out my password. Then you realize, oh, it's a student ID with an exclamation point in front of it or at the end of it or in the middle of it. You know, that's what people do. So passwords really need to be kept secret and safe. Now, this is never write it down. I want to point out that I will tell people quite often that if they have a password for their Wi-Fi, right, especially those folks that are older, I'll tell them, oh yeah, people are going to come in and want to get on your Wi-Fi. It's okay for you to write that down. And they'll go, really? You know, because that's a password, you shouldn't write it down. Well, it's true, but you know, if I'm in your house, I'm going to get on your Wi-Fi. You know, I could just go reset the box, right? I'm in your house, so I could see your password there, or I could just go reset it and make up my own stuff. I mean, that's really not really helping you much. That's just a little tip that when you're talking to people, it really depends on what you're trying to do. You don't write your passwords down for all your accounts and leave them someplace so that people can just go, oh, there they are. I've known a lot of people that have done that. So a good password should be 16 or more characters. So it's best to think of a passphrase like the little brown fox jumped over the lazy dog, maybe not that long. Put a special character in there. Also choose a password that would be difficult to guess. So don't include your birthday, your anniversaries, names of family members. Those are all poor choices. I will tell you honestly, I use a password or several passwords, obviously, and they have certain commonalities to them that mean something to me, but they don't even mean anything to people that know me. The people that know me wouldn't even naturally guess, oh, that's probably his password. Something that has meaning to me in the past, not an anniversary or anything like that, but it helps me remember it, but nobody else knows how to even get that. You have to ask me a lot of questions, and you'd have to be on the right track in those questions to get anywhere. Anyway, it also says use unique passwords for every account you have. And that's true. We should do that. Most people don't do that because that's very hard. That's why I mentioned 1Password and those kinds of things. If you've always got your phone with you, right? Apple has built-in keychain. And anytime I create an account, it'll pop up and say, use this really weird password. And that's what it wants me to do. And if I've always got my phone, then that's fine because I can always get into that site with that really weird password. That keychain is passed along to my iPad, to my Mac, to anything that I want it passed along to. That way I can have all these unique, really long passwords. A cross-platform version of that is 1Password, where basically you log into 1Password and you pay them and you have a really good, strong password protecting that account. And it keeps track of all of those passwords that are all different. You don't even need to know what they are. And then that way, when you hit the site, 1Password pops up and goes, yeah, I know what this password is, and it puts it in for you. And that's a way to keep unique passwords for every account and actually make it work for you. And that's what a password manager does here. I'll let you look at group policies that has to do with working in businesses and resetting and all those different things. Again, I don't want to totally duplicate what they're talking about because then you'll be really frustrated. The other thing I want to talk about here is Windows Firewall and business continuity and fault tolerance. And I thought, there we are, I clicked on the wrong thing. So Windows Firewall is Windows Defender, and it's built in, and it is a full-fledged firewall. That's one thing I want to mention, but I want to mention again that Windows Firewall is turned on. It's on unless you turn it off, and then it'll just keep warning you that you turned it off and you're in trouble, right? It'll keep doing that. But as soon as you connect to a network, whether it's plugging it in or through Wi-Fi, it will ask you some simple questions. And it'll say, hey, is this a private network or are you on a public network? What are you on? And that'll set all the firewall rules for you very easily. Because if you're on a public network, you want your firewall to be stronger. You want those settings higher. If you're on a private network, then you want to be able to share files and find printers, and you want that lower. And it sets it up really good for you. It is very hard to switch that out. And some of you will go, oh, it's not. You can go in there and just flip the switch. And I will tell you in class, as we've done this over and over again, a lot of times just flipping the switch and telling it, oh yeah, this is not a public network, it's a private network, won't work. And it causes some issues. So try to get that right when it asks you about that question. And I would suggest you go into Windows Defender if you're into security or want to get into security, and take a look at what's in there. You don't necessarily have to touch anything, right? You could just go in and look and say, what are these settings and what is this telling me? That'll just kind of get your mind in the mode of, hey, I can start figuring this out. And they show you some, little default settings that you can run through. All right, fault tolerance is a big thing, and that's why I want to talk about it. Fault tolerance means I want to make sure that whatever device I'm using does not go down. Now, for us, we can't afford to do that with everything that we do. In other words, you don't keep another phone in a box just in case this one quits on you. That's just too expensive to deal with. Same with computers. But when you start dealing with bigger systems, you start dealing with technology where you're hitting thousands and thousands of servers. One of the reasons you're hitting those thousands of servers is not just because of load, of how much need there is to give out that information, like Chase. I always use Chase as an example, but also that it's fault tolerant. They have different sites so that if one whole site goes down, there's another site that will answer your questions. Right? Within the site, they'll have fault tolerance operating. And that really means I have certain things in my computer that might fail. So I'm going to have backups for them. A good way to look at it is hard drive. And I think they mentioned RAID down here. No, they don't. But RAID is part of that, of saying I've got all these mechanical drives, and mechanical things tend to fail, and these hard drives are always being used. So I'm going to have this one and it'll be working all the time. And then this one will be my backup. And if this one goes down, this one will kick on and take its place. That's fault tolerance. Data redundancy, network redundancy, power redundancy. So a data center is an area used to store such things as computers, applications, data, component, switches, and routers. These data centers may be a room or a building, an entire building, a group of buildings. Data centers are the main areas of focus when implementing fault tolerance. And again, that's the example I gave. They may have, Chase does have, Apple does have, Google does have. All these massive organizations have different data centers. That way, if a whole data center can't talk to the internet, you've got another one. And then within the data centers, they've got all these hard drives with backup hard drives running, and they've got servers with other servers just sitting there not doing much. And then if one dies, another one will kick in. Right. So data redundancy, that's RAID, redundant array of independent disks. That's what RAID stands for. And that enables you to put in several hard drives where basically if you have one drive fail, you can replace it. Network redundancy, sorry, here we are. Multiple servers or multiple network interface cards in the servers, multiple pathways between the servers and the computers in case one of the network cards dies and you need another one to get working. You can go into networking and then specialize just in this type of work. just in redundancy and making sure that the computer systems that are going in and being put into these places have exactly what they need. And talked about site redundancy, and then of course power redundancy. You usually will have an uninterruptible power supply called an UPS. We usually don't call them UPSs, we call them UPS. So that's one thing. And then those organizations will also have at each building a mega diesel generator. So you put diesel fuel in it, and the power it's powering the whole facility through diesel fuel until the electrical comes over. Failover is seen in the previous example. Having redundancy can be very beneficial. An important part of redundancy is ability to switch to the redundant component. So you can have the redundant stuff sitting there, right? I can have the diesel engine sitting out there, but if I don't have a mechanism for kicking the diesel engine on when it's needed, it's not helping me. If I don't have a mechanism for using the extra hard drives, such as I use RAID, then it's not really helping me. I will still have to take the system down and replace the hard drive and restore it back up, where RAID enables you to just have it running full time. And that's what failover means. When a redundant system kicks automatically over to the new, better stuff, the working stuff, it's known as failover. Right, I think that's it for this one. Oh, wait, there's some RAID implementations. You're like, oh no, he was going to be over and now he's not. Yeah, so sorry. By the time we get to this point in our learning, it's like, what more is there, right? What more? There's a lot more. And hopefully that excites you, and hopefully you're not too drowning in it. Your brain works. Trust me, it works. Just get the information in there and keep learning. It's important for your success to just realize I'm not going to fail at this. That it's just about time and putting in the time and effort to make sure I get all the information in my head the way it needs to be. So one of the things here with RAID is yeah, it was first used in the late 80s when they realized they could get better performance with an array of inexpensive drives. Basically, there was a couple of things happening. Hard drives were so expensive, really expensive. So it was cheaper to buy a whole bunch of small drives and then make them act as one. Now, that's not something we did on our computer systems. I didn't have a computer system with 5 drives in it. That would have been, wow, I would have had some money. But on servers, they did that. And since all the computers had very limited storage, putting a bunch of these drives on a server meant that you could offload what you had on your computer to the server. And so they would get a bunch of them, but they needed them to behave like one. They needed people to be able to go to one storage space and see a bunch of places they could put stuff. Not, oh, I got like 16 different places I can go. No, we need it to be one. And then they, of course, realized, hey, when we do this, if one drive is busy writing what James McBride is sending, there's another drive free to write what somebody else is sending. And so it actually is faster to do. And that's where RAID began. It really began with, we can speed up this process. And the more disks they had available dealing with hard disks, the faster they could make it to a point. And that's what it became. Then, of course, later on, you start to realize, well, these hard disks do die, and that's a problem. So we can also start to duplicate the data across this array. That's what they call it. We put 10 of these drives together in an array and they all act like one. That's great. We got the performance boost. But what if we actually use some of that space to back up information from other drives? So you see here, they've got A1, A2, A3, and then AP, or lowercase p there. I'm not a big math person, so sorry. And what's happening is it's saying, okay, well, what we're going to do is this is the storage that we're using, and we're going to take and smash that stuff down into another area on this other drive, and we're going to stripe this. That's what they call it. So we're striping across these volumes. And then notice what they did with B2, but we're not doing 3 here. We're going to do that over here. That way, see, the backup is being spread across different disks, and that's what you can look at here. So you don't actually, with RAID 5, ever get the full space. If this is a terabyte, 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 and terabyte, you basically subtract a terabyte from that because there's a terabyte being used for backup. So you would have 3 terabytes as part of this RAID 5, even though there's actually 4, but that last terabyte is being used to spread that backup across. Now, what this means, and is fantastic, I've seen it work, I've done it, is that if this drive dies, this drive can be taken out, removed, and these will continue to work. They'll automatically be able to access all the data because you have that special little backup going. Then you can come in and push in a brand new drive, which in this day and age, they'll have just spares sitting there if this ever happens. And they just pump that straight in there, lock it in place. And the RAID 5 will actually start to take the data out of these locations and rebuild the array. That's what they call it. So it'll rebuild it just like it was before. And it'll slow down the system a little bit because it's doing all these rebuildings on the hard drives. But once it's done, you're back working like you had before, and you have a whole extra disk in case something dies, which is fantastic. So you're getting the speed of striping it across these different hard disks because they're all moving, they're all working, and you also get the data redundancy that you need. And that's fault tolerance. And you get performance and, of course, increased capacity. Now, there is a difference between striping and mirroring. Now, what we were looking at is parity. Striping means that it's just putting this across different disks. And I didn't really explain that, but I kind of used it in a sentence, basically. So you're taking the data and going, this one's free, so I put information here, and I put information here, now I put information here, and that's striping. RAID 0 basically is just using 2 disks, and it stripes the information, A1, A2, A3, A4, A5, A6, and you get a performance boost. You can see that there is actually no data protection here. A RAID 1 is mirroring, meaning whatever I write to disk 0, I'm going to write to disk 1. Now you're not getting the performance benefit of striping, but you are getting the data redundancy. And this is used a lot. Lots of systems will use that as, okay, these are my drives that I boot up off of, and they're my system drives. And then my data drives are actually going to be striped. So very, very common to have. This is RAID 1. That's where my server OS boots and all that stuff. And then here's my RAID 5 volume that's got all these other disks in it that it stripes across. This does not give you the performance benefit. All right, so parity. Parity is another way to help protect against data loss, in which data can be recalculated with the help of other drives if one fails. And that's what that little P stands for, is the parity that's being put on. That's where your parity information is. Now, in order to do this, you have to have an actual hard disk controller or a storage controller, however you want to put it, that understands RAID, that can deal with RAID. And we actually have those. Hopefully, it really depends on our time that we get. But one of the in-class, hands-on labs we do is dealing with a little controller that I have that allows you to plug in 4 SATAs and see RAID work. So we have time, we do that. And it actually understands 0, 1, and 5, and maybe 10, but I'm not sure about that. So in other words, you have to have a special set of chips that understand how the data is coming in and where the data needs to be put. You can't just do it by plugging in SATA. Some boards, some home computer boards, main boards, motherboards will actually have RAID built in. I would suggest you don't use it. I've seen those flake out, and you don't need it. You really don't. But you have to have a RAID controller. And of course, those can be very expensive. They can be $5,000, $6,000 because they're very, very fast, very fast. So these are the different RAIDs. We use 0, we use 1, we use 5, and then we use 10. They're not listing all the RAIDs here. I guess we'll learn that in the other class, which is a combination. 10 is a combination of things. But those are the main ones we use. The others were created for different different things, like 4 incorporates block level striping, meaning that it's writing a whole block of data. We won't get into that. That might be interesting to me, but you may not like to hear it. So, and it's not part of something you need to know. So let me look at, now you can, I'll let you go through that, through their information. Because backup stuff I would talk about would have to do with the incremental backups, differential backups, that kind of thing. Disaster recovery facts. This is kind of a big one, a general topic, something that every business has to think about, and really came into being around 9/11, when tons of communications were taken out. And we obviously should focus on the loss of life that happened in 9/11. And we focus on that so much that nobody really talks about the jobs that people and the lost money, and that really affected other people's lives, that maybe they didn't lose somebody, but they lost their job, or they were out of work for months. And the reason why is because when something like that happened, all those businesses that were in that building, if they didn't have a disaster recovery plan, it took them years to come back. And, we can talk about businesses separately and say that, the evil of the man that's running the business, but that does boil down to, do you have a place to go to work? And if you don't have a place to go to work, how are you paying your bills? And that's what disaster recovery really comes down to, is trying to make sure that whatever the organization or company does, they can continue if a major disaster happens, because you are talking about people's welfare. You are talking about, COVID killed businesses, right? There's tons of businesses that have never come back from that because they could not stay in business. There was no flow of money. That's a disaster that happened to them. Larger businesses had something in place where they could try to mitigate, try to lessen the effects of that disaster so that they could stay in business and still be able to pay their tens of thousands of employees. So a business continuity plan is basically, how do we continue our functioning? What is it that we do, that we have to do, to make sure that we can continue? I like to use EAC as an example. That would basically for us be, how do we continue to teach? We have students that come in, right? This happened to us with COVID. We have students that come in and they're going to get credit, and they've gotten money from the feds, or they've paid themselves. And it's their livelihood that they're investing in coming to school. And then COVID happens. And then the government regulations come down. And then you have to comply with this, this, and this. Well, how do we continue to teach you? Because at the end of the day, you need to be able to get a credit, a grade for that course. Otherwise, the money that you invested is lost, and that's not beneficial to you. So we had to have, they worked very hard, honestly, management here worked really hard on trying to comply with federal and state and local mandates and make sure that we could still give you the class that you needed. That's a big business continuity plan. Another thing that they probably have is probably the biggest thing that could affect EA is having that area flooded. There's an earthen dam up there above where EAC is, and if that ever broke or stemmed over, it would just wash down through that area. And they, I'm sure, have a plan in place, like, what do we do? How do we make sure that students know you can continue to get credit? The internet, of course, has made that a lot easier for us, but in some organizations, it's not that easy. And they go through a process of prioritizing. What do we need to actually function? We need our email system. We need the financial system. We need our customer relationships management system. They define what are the most important things or sets of data that we need to be able to get to. Restoring data is often a part of that, and then restoring access to that data. A lot of places will have hot sites, that meaning they just can move their entire organization to that other place, which is really, really cool. Well, that is it for just the introduction to cybersecurity that I wanted to talk about. There is a ton of stuff in here that I haven't gone over So if you got questions, then please let me know, because I'm more than willing to do another little video or talk to you directly, or however we want to do it. So don't say, well, you didn't cover that and now I'm just lost. Don't do that. I'm trying to hit the sweet spot where I'm giving you enough information for you to get through, plus the information you're getting from them, and I'm not overdoing it. So if you have questions on anything, then ask me and I will help you out.